Hello students. So today we are going to have the last part of the gravitational chapter. So in the last part we will be dealing with the gravitational acceleration g. Now most of us has used already the value of g like 9.8 meter per second square, or sometime you also take this as 10. But is it so? Like, we know that Earth is not round at all. So Earth is not round. These two sides are little bit elongated, and then also there is like non-uniform, what you say, uh, circumference, or the you can say the surface is not as same as like this because there are oceans. So oceans are like craters. So actual shape looks very weird actually, but looking from outside, it seemed to be round. Now, because the earth is not like uniform in nature, that's why the value of g also varies in like differently. Like, we have a variety of g values. Whenever we come from equator to the pole, the g value changes also. Now, why and how the g values changes, we will be talking with that. Now, till now we learned that the force given by gravitation is g m by r square. R is the center of the distance between center of masses of two mass, which is one is big M, one is small m. Now, as we know, this is equal to also mass into acceleration. So in this case, I'm talking about the acceleration of Earth. So if I take the acceleration of Earth, it will be this, and if I take the acceleration of this thing, what you say, the object, then it will be mg. Now, very interesting thing we will see here, that let's say we have Earth here, and we have a small object also. This is m, Earth is big M, and the distance between the center of masses is r. Now, we know that the force is mass into acceleration. Also, we know that the force due to gravity attracts each other. So, the force given by the Earth on the small object m, small m, will be this way, and the small object m will also attract Earth. So the attractional pull will be this way. So if I give the name of the points, so Earth is having force AP, whereas the force given by this small m is m into, sorry, is PA in nature. So the forces are equal but in opposite in nature, in direction. So we can always write here for these individual forces, I can write this is mass into acceleration. So now for small m, I can always write this is small m into the acceleration of small m, which we take as g generally, because when something falls into the earth, we take the acceleration as g. If we write the acceleration of this big mass m, that is the earth, then we have to write the big mass m and the acceleration of earth. Now, why earth is having acceleration? Because it may be negligible, but still earth will also try to come towards this small mass m. Okay, so generally we will be having this two things. Now, if I just remove this part, you can easily see here that this two portion, you can just take a look. So I can write mg is ma. So the acceleration of earth is mg by big M. Now we know that the mass of earth is very very big compared to the object, so m is very very small than m, right? As a result, this ratio is very small, very small. So the value of this a, that is the earth acceleration, that means like how much with how much what is the change in velocity of earth towards that object is also negligible. So that's why if you drop a stone or something in the earth, then you don't see that earth is coming to the stone, rather you see that the stone is just falling to the earth. Why this is happening? Because this acceleration of earth, like how in what is the change in velocity of earth towards that what you say stone is also very negligible. You will not be able to notice it only. So that's why we don't see that earth is coming to the stone, rather we see that the stone is falling to the earth. Now, talking about G. So now G varies is, first thing we will see here that if we take only this much, what do we get? So this we get Gmm by r square is equal to uh, m and g. So mm will go and we get Gm by r square. So this is a vital thing. We have to remember this. So G is Gm by r square. What is r? R is the distance between the center of masses of two objects. Now, as a result, whenever we have Earth, so I should not draw with this. I should draw with, yeah, Earth is a blue planet. So if we draw the Earth, so if we go little bit up from the Earth surface, if we go up and if we go down, in both cases the value of G will change. Now we will see how this value of G will change, and in how we can predict also. So let us find that if we go a little bit higher, so let's say we are trying to find if we go at some distance height, then what will happen? So if we go from here, okay, let me change the color. Okay, so if we go at a height, let's say h from the Earth's surface, so this is our h, this is the radius of Earth, and here is my object, and I want to find what is the value of G at point P, and this is the value of, so this is S, the surface. Okay, let's say the value of G in the surface is G0 or GS, whatever you can take. So according to the formula, we know that G is Gm by r square. So instead of r square, I can write here Gm by r plus h square. Okay, so I can write like that. Now one thing you see here, that if we take this thing up, so I can write this. Let me simplify more first. Okay, so what else we can write? We can write like this, Gm by, so from here I can take common r. So if r comes out, it will be r square, and then we will have this r by h by r square. Okay, and from this we can also write, now you can see this part. This part is nothing but your G0, matlab when your h is 0, so your r is the distance, so that we call as the value of G at our surface. So this is Gm by r square. So I can write here G0. This part I can take upside, and I can write like this. So in the next line I can do, so what I have gotten? I have gotten this G0, then 1 plus h by r to the power minus 2. We have gotten this. So if we do binomial expansion, binomial expansion. So I can approximate this as, so binomial expansion is there in your mathematics, so you can see from here. And I can approximate some formula like this. So if you forget also this formula, you can start up with this. You can use this formula for accurate result, no problem at all. So if you forget also, you can use this formula. Okay. Acha. Now, ultimately after approximation, we have gotten this. So I can see that as my h is increasing, this term is increasing. As a result, this whole term is decreasing. As a result, the value of g is decreasing. So once you go upside, the value of g decreases. Okay, the value of g decreases, and this is the formula we can use to find out what will be the value of g at any certain height. Okay, so we have talked about what will happen to g when we go upside, but what will happen to g when we go inside? So let us draw one more earth like this, and let us take that we are going inside earth, and we have come at like some depth. So this is our r, and let's say I have come till here, so the depth is d. Okay, so the depth is d, this full, so d is this much and r is this much. Okay, so one thing I will have to write, so similarly I will write that formula gm by r square, because that is my initial startup. I can write here gm by, now this r will be the big R minus d square, right? You can see from here only. Now here I cannot use this m. Why I cannot use this m? Because whenever the object is here inside, only a certain portion of your earth, that means this much, wait just a minute, yeah, only this inside portion of the earth will be able to attract this. Okay, the outside portion is already excluded because the object has come inside. Okay, now you can tell that, sir, this object, if this object is, let me put a dot, otherwise it's not visible. Okay, so this object, okay, this violet object, this object will be attracted by these things also, right? But one thing you will see that this certain object will be attracted in different directions. So the up, just above the object, that thing will attract upside. This part will attract this side, this part this side, downside also. But you can see that this part, you can tell that, sir, this thing is so big, maybe this thing is so small, maybe, so what will happen? But the direction is opposite and they cancel each other ultimately. Okay, so you don't have to bother about that. You can see by doing calculations. It's up to you. You can see, you can check, but that's a rigorous thing to do. So we are just taking that logic. The outside portion, this portion of the earth, will not attract that violet object. Only the inside portion will attract. So this m will be changed. So I am writing it's m prime. So we have to find out what is this m prime. Now, if the total what you say, volume of the so we, let's say volume of the earth is 4/3 pi big R cubed, and the mass is big M. So the density rho will be, we know that mass is density into volume, so we can write mass by volume. So I can write it this by 3 will go up pi r cube, right? and so we have to find this much. So the radius you can see here, r minus d, so that means the mass m prime will be volume into density. So the volume is 4 by 3 pi. Now see, what is the radius this much? This much is my r minus d. So this will be r minus d cube. Okay. And the rho is my 3m by 4 pi r cube. Right. So you can see here that this things will cancel each other, and ultimately what I will get, so I'm writing here, so I will get m r minus d cube by r cube. So if I use this formula and I put the value of m prime here, what I will get? So I'm writing it here. G is G. Now instead of m prime I will write, so downside it was r minus d whole square. So this is r minus d whole square. Okay, m prime is m r minus d, and then we have cube divided by r cube, right? Okay. Now you can see that we can cut this, and finally we will get gm by r cube r minus d, right? And from this we can also write gm by r square, sorry, and we can take one r inside and we can write 1 minus d by r. So what I have done, I have just multiplied this denominator with them. So this part is again my surface gravitational acceleration. So from this I can get the formula. G is gs, that is the surface, or go, we have taken go. So 1 minus d by r. So you can see here that this will happen when you go inside. So if we go inside, then also g decreases. If we go upside, then also g decreases. But if I go upside, g decreases more. But if I go downside, g decreases in a less rate. Okay. So if we just draw, so I'm just writing this two formula together. So g is my g0, 1 minus 2h by r, as far I remember. Yes. And this is for height, and g is equal to g0, 1 minus d by h, sorry, d by r. This is for depth. So what is the graph? The graph will be like this. This is my so this is my distance, which is increasing from the core of Earth. So at the core of Earth, the value of g is 0. You know that, because this d will be r at the core of r, and that's why this part will be 1. 1 minus 1 is 0. Why d will be r? Because you can see here, if I go, if my d is this much, if I am at center, then my d and r will be same. Okay. Acha. So this will start from 0. This will go like this, and then it will just decrease like this. Okay. Because the rate is higher in this case, so it will decrease like that. Okay. And this is my value of g. So where it is highest? At surface. So at surface the value of g is highest. Okay. So this happened to g. Acha. Now you can tell me one more thing. That is the last part. What will happen to equator and the poles? So let us draw and try to understand. Acha, I'm drawing not this one. I'm drawing this one because Earth will be a little bit like that. Okay. let's say I'm taking the axis to be as my reference. I'm taking this as like this. Okay, I know that Earth rotates in a tilted way, but if I tilt my head also, I will see straight only, so no problem. Acha, now the question is that you can see here that here if any object is there, then if there is no gravitational pull, as Earth is rotating, the object will have a centrifugal force, right? So the object will have a centrifugal force. So what will happen to the object? The object will fly into the space, right? So it will go into the space. Does it happen? No, it does not happen. So what is necessary to hold the object? To hold the object, Earth has to give more force, right? Now you can see that when the Earth is like oval and these two sides are compressed little bit, so more masses are there in these portions, right? I'm just trying to tell you that if you have something like this and here you have this, and if you have something like this and here you have this, where the pull will be more? Obviously in this case, because the you can see here the concentration of mass is little bit concentrated, but here the mass is distributed, so it will attract like this, and there will be resultant. But here the resultant is more because it is not distributed, it is concentrated. So when Earth is little bit, what you say, flat, like compressed in suppressed in up and top portion, top and bottom portion. So what happened? The mass is more here, and you can see this is the miracle of nature, that it needs more force, and automatically due to what you say rotation, the mass concentration is also high here. So ultimately, this force, it is gmm by r square. So I can write is mass into acceleration of this object, right? Of this object. So I can write this. So this mass into acceleration has to be high enough to balance. So this mg, this has to be mv square by r. So g must be v square by r. Okay, this must. But if you talk about the pole portion, you see in the pole there is no centrifugal force, right? Only that, only the gravitational pull is there. And as a result, because the mass is distributed here, you can see the flat, the this portion of mass is a little bit flat. So that's why the pull is also not concentrated. So as a result, this mg is lazy. It does not have to do anything. Okay, so this is for pole, this is for equator. So the pole one does not have to what do you say, counteract anything else. Only he is there. Okay, he does not have to counteract, and that's why the value of g at pole is also less automatically. And the cause is this one, because the mass is not concentrated. Okay, so these things are there. Okay, in your what you say, gravitational field. This much is needed. If I missed some topic, I'll be covering up in the live classes, uh, and do some numericals. We will practice more numericals. Uh, and what to say? Acha, this law, you can ask me. So this Newton's law is valid how much? Like, what is the limitation? Yeah, this is also limited. Like, this law is also limited to its like certain extent. If you go very near to a very massive object like black hole or neutron star, very massive objects, then this law will not work. This law will work for moderate to semi-moderate planetary systems, and you know that for the subatomic particles, even this force is very weak. So yeah, it plays a role in quantum gravity. You will see also, but yeah, like in the extreme small cases and in the extreme big cases, this law will not work. So this much is there to tell, and there are more interesting things about gravity because astrophysics deals with gravity all the time. So whenever it is possible, we'll be talking about that. So bye bye for today, and we will see in the next class.